Hello, welcome to Chapter 2, Episode 6b, and today we're going to be talking about solving exact differential equations. So, suppose you have this exact differential equation here. Let's think about how you can go about solving this. So, remember, we have some function f such that pretty much the gradient of f, okay, is equal to m and n, okay? So m is equal to f, the partial derivative of f with respect to t, and n is the partial derivative of f with respect to y. Okay, and then obviously this t could be x if you wanted to. I'm just using t because that's what's in my notes. So what we want to do is we want to solve this equation. We kind of want to find f. So how can we find f? So the way to do this is if we work backwards, okay? So we can find f as the integral of m times dt, which is going to give us, there's going to be some integral but plus, and then we want to make sure, since this is just the general antiderivative, we need to include this constant function, right? But notice m is a function, okay, m is a function, so the f is a function of t and y. So m is a function of t and y too, right? So we're integrating over dt, but we're not integrating over y. So when with this constant term is a function of y. So since we have since we're treating, if we were taking the partial derivative with respect to t, we would treat all the y terms as constant, right? So we find this cy, right? So the next thing we want to do is, well, we know this other identity that, well, f of y is equal to n. So let's take f of y, which is going to be equal to the partial derivative with respect to y of m dt plus c prime of y, right? And this is equal to n, right? So we're saying that this is equal to n. So we can solve for cy now. So we can basically go, okay, cy is going to be this integral of n minus partial derivative with respect to y of our integral of m dt. And then obviously this is all kind of encapsulated in that integral. Dy. And right? And so we can solve for cy here. And then once you've solved for cy, we've essentially found f, since we can take the integral of m and you take the integral of cy. We can do literally the exact same thing with f, okay? If we started with n, so start with n. So do the same thing. F is equal to the integral of n dy plus c as a function of t, which is obviously we get f of t is equal to partial of t of our integral n dy plus c prime of t, which is equal to m. And then we can solve for c of t, which is equal to this big integral of m minus the partial derivative with respect to t of n dy, and then all times dt, right? And then so we basically get this equation. So f is equal to, and there's going to be two formulas here, m dt plus this integral n minus partial y m dt dy, or f is equal to n dy plus, and we have this big integral here, m minus partial over partial y and dy dt. Okay, and so this is how we can solve that. But obviously this only works if m is equal to f of t and n is equal to some f of y, right? And so remember, that's only going to be true because of the equality of mixed partials, right? We have this equality f of ty is equal to f of yt. So in order to check for this, all we need to do is go, okay, m of y is equal to n of t. And if this is true, then we can use this formula. And I think that's pretty much it. Thank you for watching. Next, I'm going to actually look into how we can use this to solve some problems.